Uh, Good morning, everyone. I am Ashok Shaw, a postdoctoral fellow at the University of Guelph, working with Professor Emmanuel Arnaud. Before I start, I would like to thank our team members and Ontario Groundwater Geoscience Open House for providing such an incredible platform for early career researchers like me to present our work in front of you. Our work is a collaboration between Matrix Solutions and the University of Guelph, aiming to improve the Quaternary geological and hydrostratigraphic model used to drive City of Guelph's drinking water source protection agenda. So this map shows our model boundary, which is naturally bounded by groundwater flow limits, the Grand River to the west and the Niagara escarpment to the east. Although our focus is in Guelph region, the nearby overburden areas are crucial for recharging the city's bedrock aquifers. Now, the city of Guelph has been committed to protecting its groundwater resources. For many years, in 1999, it developed its first groundwater flow model, which has been continuously upgraded with the inclusion of new data sets. And our current project builds on over these 2 decades of progress and further improving the model by characterizing overburden sediment heterogeneity to inform groundwater flow dynamics. This support the City of Guelph's One Water plan. Since the City of Guelph sits on quaternary sediments, it is useful to characterize, to understand its characteristics rather, in order to predict the shallow groundwater flow, surface water groundwater interactions, as well as recharge rates and groundwater contamination risks, so on. The previous existing models, they oversimplified the region's overburden geology, lacking essential details of spatial variability and sediment heterogeneity, and so a detailed framework was necessary. We took several steps to develop our 3-dimensional geological model. First, we collected data from different borehole records available in this region. Next, we simplified and standardized the descriptions of lithological properties. Then we assigned stratigraphic units to each borehole intervals. And finally, with this all collected informations, we developed our 3-dimensional model with the help of Leapfrog software. Let's talk about the data set. Around 31,150 borehole records were digitized so far using different sources. This map shows the distribution of 54 high-quality boreholes. This data mainly comes from Ontario Geological Survey as well as Morwick GT60. Now, this map represents almost 1,300 medium-quality boreholes, mainly sourced from geotechnical reports, which are often practical, which contain practical but less detailed geological or sedimentological informations. And finally, this one reflects the distribution of low-quality boreholes taken from nearly 29,800 water well records, and which are less consistent in accuracy but provide a wide coverage across the region. Now, after digitizing the borehole records, the next step was to standardize lithological descriptions. So descriptions from different borehole records were combined and standardized into 15 main lithological characteristics. These logs here represents the difference between the original and the updated one after assigning these new lithological categories. For example, clay and silt were grouped together into a new category named mud. So this made the data more consistent and easier to compare, thus forming a solid foundation for the development of our geological model. Now, after standardization of these lithological properties, stratigraphic units were assigned based on several factors. First, we used the existing stratigraphic framework of the region. These are based on previous studies and provide us a sense of what we can expect in the subsurface of this region. So here, the Waterloo and the Orangeville geological model, they are sourced from Ontario Geological Survey dataset, and they represent the subsurface in the southwestern and the northern part of our model domain, while the lower one is from the Guelph region, and it is based on Modwick G360 database, and they provide geological model for the southeastern part of our model domain. So second, we used our understanding of glacial depositional environments and the expected sedimentary types and geometries to inform our stratigraphic peaks. Here, this diagram, for example, reflects complex ice marginal geological settings and their associated sedimentary deposits. Physiographic surfaces also considered to assign the stratigraphic peaks. The physiographic elements are classified based on their mode of deposition and appearance on the surface. They are like flat depositional elements like till plain, outwash sand and gravel plain or clay plain, while positive topographic features are drumlins, eskers, and moraines. And finally, the erosional elements like buried valleys. So to connect with the subsurface, we utilize the physiographic elements at the surface to predict the sedimentation styles in the shallow subsurface, which includes the geometry of sedimentary types and units like associated with different physiographic elements. So for example, if we get diameters in the subsurface, and if it was under a till plane, we might expect a thick or rather extensive till sheets in the subsurface, whereas if we are near the moraine region, the discontinuous layers of sand and gravels or clays might interrupt these diameters in the subsurface. So using the regional stratigraphic framework of Ontario Geological Survey, we assigned the hydrostratigraphic units to each borehole intervals based on our understanding of regional geological settings and physiographic element-based sedimentation styles, as well as the depositional environments associated with each borehole interval. And using multiple cross sections, we started with high-quality boreholes, and use this collective information to then make most plausible interpretations and assignments for those low and medium quality boreholes. So here is a final representation of our three-dimensional geological model for city of Guelph, and you can see that it provides a much higher resolution understanding of overburden sedimentology and hydrostratigraphy within the model domain. Now to understand the impact of our Quaternary geological model, we created 3 isopack maps. Just a second. We created 3 isopack maps, which showing the thickness of 3 key hydrostratigraphic units, which are mainly found in and around the city of Guelph. The Port Stanley ATB1 aqueduct, they are mainly concentrated in the central and western part of the region, while the post-Port Stanley AFA2 aquifers, they are mainly restricted to the southern and southwestern part of the region, mainly along the Speed River Valley and all the creeks. In contrast, the youngest Wentworth ATO2 leaky aqueduct, they usually trends northeast southwest and is mainly confined to the eastern side of the Eramosa Speed River Valley. They attain their maximum thickness when they are associated with Paris and Gold moraine. Now on the right side, you can see there are 2 cross sections. In the upper corner, in the top, in the upper corner, this one is the old subsurface geological model, while in the middle, this one is our newly developed model, and which clearly shows that, a much detailed distribution of hydrostratigraphic units and their expected sedimentary geometries and potential pathways or potential connectivity to the underlying bedrock. Now, this refined geological understanding is very crucial for assessing the groundwater contamination risks. Like, for example, if a spill occurs near the Doyle Drive, it could easily reach the Guelph bedrock aquifer because of the presence of highly permeable AFA2 outwards aquifer in the subsurface. Now, there's another cross section, and this cross section provides another example of how our model, can be used to inform groundwater resource management through quaternary geological insight. Here in this cross section, we can see that how the dark green color, that ATB1, the shallow ATB1 Port Stanley aqueduct, may restrict the downward infiltration, which leads to the formation of water, leading to the water accumulation and formation of wetland, especially between the side road 10 and East View Road, for example. And additionally, we can see there are buried valleys in these cross sections, and depending on the nature of the infill, this can act as a potential pathways of contaminants between the surface and the underlying bedrock aquifer. So this refined model, they provide much detailed information based on which proper decisions can be made for any kind of future development of oils in this region. Now, one thing we'd like to mention here, that our model is very regional scale model. So we would require additional boreholes to develop local site-specific hydrogeological investigations to better understand the local sediment heterogeneity, as well as the groundwater flow dynamics and the rate of fate and transport of the contaminants at the local scale. So for our future plans, we are currently focusing on the quaternary sediment and the bedrock interface to explore how the Pleistocene geological processes and their associated meltwater drainage influence the nature and distribution of the sediments at the interface. And this in turn will inform our understanding of modern day shallow groundwater flow systems, especially shallow bedrock groundwater flow systems. Last but not the least, we always welcome collaboration, as sharing our ideas with other researchers can lead to valuable discussions, more insight, and strong connections in this field. So I'd like to acknowledge the fund support from MITRA's Elevate Postdoctoral Fellowships in partnership with Matrix Solutions and NSERC. We also benefited from our discussions at data sharing with City of Guelph and Laura Weaver from Morrick G360. Thank you very much for your support. Thank you.